Okay, so in this video, I'm going to cover the section 3.3, divided differences. Okay, in my lecture note, it says 3.2 because I made this when I made this lecture note using the older version of textbook. That's why the section number is 3.2. But in the current version of textbook, the divide differences in section 3.3. So in this section, we're gonna develop the Lagrange interpolating polynomial in other way, so alternative way, kind of. So see, suppose that p of x, suppose that p of x is the nth Lagrange polynomial that agree with the function f at the distinct numbers x0 to xn, and we want to express Lagrange polynomial as like this. See, okay. So it's called the algebraic expression. This is alternative algebraic expression. Okay. So now then, let's see right here. Okay. So then we need to find out the constants a0 through the an. You see. Okay. So how can I find out a0 through an? We're gonna use the property of Lagrange polynomial, which is what? The p and x must be equal to, I mean, p and x must agree with the function f at each node, right? So we're gonna plug in x0 through the xn. Okay, then we're gonna get we can figure out the constants a0 through an. So let's see. Okay. So when you plug in a0 into x right there, okay. So now then, plug in the a0 into x, then we'll get the a0 equals pn of x0 equals f of x0. Okay. So, and then because you see, now because the x minus x0, oops, see, x minus x0 is included all of terms except for the first term a0. So when x is x0, then all of term going to be 0 except for a0. So Pn of x0 is equal to a0, and then that must be equal to f of x0, right? So f of x0 is a known, okay? This is given. So we figured out a0. Now, when you we're going to plug in x sub 1 into the x. Then the first two term going to be left, right? And then we know that what a0 is nothing but f of x0, right? Okay. So f of x0 plus a times x1 minus x0 is equal to must be equal to f of x1. Then we solve the equation for a1 because we know f of x0, we know f of x1. So a sub 1 is the only letter which is unknown, right? So then we got this. a1 is equal to f of x1 minus f of x0 over x minus x0. Now, then what? So now we're gonna we're gonna repeat this process to figure out all the constants a0 through an. Okay, so that's the divide and then that's the then we that lead us to the divide difference algorithm. Okay, first one, I'm gonna introduce divide difference notation. So the zeros divide difference, the what does that mean? Zero. Zeros means the degree is 0. Okay, and then f of bracket xi. Keep in mind is that doesn't mean the function value at xi. Okay, so that's the notation of divide difference. Okay, xi is equal to f of xi, and then first the divide difference, f of xi comma xi plus 1. I mean bracket x sub I comma x. This is defined by like that. Okay, but I mean out of blue, where that comes from? So when you we could express, see that f of x1 minus f of x0 over x1 minus x sub 0 in terms of the divided differences, right? Does it make sense? Because when I equals 0, just substitute 0 into I, then we're going to get f of bracket x sub 0 comma x sub 1 is equal to f of x sub 1 minus f of x sub 0. But f of x sub 1, I mean f of bracket x sub 1 is nothing but what? Zero's divide difference, which is f of x sub I, right? And the f bracket x sub I gonna be what? 0 gonna be what? F of x 0. So we could express this one using the first divide difference. Okay, and then also the f of x0, you see, can be expressed as zero's divide difference. Okay, so now and the next one. So what about the second divide difference? F of xi comma xi plus 1 comma xi plus 2, that is equal to we define this one is defined as the what, f of bracket x sub I plus 1 comma xi x sub I plus 2 minus f of bracket x sub I comma x sub I plus 1 over x sub I plus 2 minus x sub I. Okay, so just keep doing. I mean, this is the first divide difference, right? Okay, so this is the first divided difference using x sub I plus 1 and xi sub x sub I plus 2, right? And then f of bracket x sub I comma xi plus 2, this is the first divide difference using x sub I and excuse me, x sub I plus 1. Okay, so keep doing that. Then excuse me, then case divide difference can be defined as k minus 1 divide difference using the second to the kth the nose, and the minus f of bracket. I mean, this is the case minus k minus 1's divide difference. Defined using the what, first to the k minus 1th. Okay, nose, right? So now actually as you see that this is equal to, by the way, let me see, it's not really easy, but we can figure out that actually this is equal to a sub 2, okay, and then this is equal to a sub k, okay. Okay, all right. So now this is simple, just applying the algebra, just doing algebra, then we can figure out that. Okay, so why this is equal to this, then just let me see, in the previous page we plug in x sub 2 into the Lagrange polynomial p sub n. Okay, and then setting that is equal to, equating this is equal to f of x sub 2, and then solve that equation for a sub 2, then you're gonna get the you can express the the fraction in terms of the second divide difference. Okay, so here the goal is to find out the zeros through the kth divided differences. Okay, so the process ends with a single nth divide difference. Yes. Okay, so that's going to be this. This going to be what, a sub n. Okay, so I told you here the we want to find out the constants a0 through an. That is nothing but finding zeroth through the nth divided difference. Okay, so now let's express the constants of p and x, the ai, in terms of the divide difference notation. Yes, I told you, right? See? Okay, so we express all the constants in terms of the divide difference notation. Yeah, we got it. So, but here's a question. You maybe wonder that why we want to express the Lorentz polynomial as like this. I mean, like this. Okay. The main reason is to that it's easy to find out the derivative of the Lorentz polynomial, and the second reason is it's easy to the established error estimate. Okay, so we'll see later. So now, let's see. All right. So now then, Pn of x. Give me a second. Yeah. All right. So Pn of x can be expressed as like this. You see, the f of the bracket. I mean, the zeros divide difference, which means the a sub 0 plus sigma. I mean, you see that here, f of x0 through the what, xk. So this is kth divide difference. That means the what, a sub k, right? A sub k times x minus x0 through the x minus xk minus 1. So k equals 1. We'll get the x minus x0 only. So, and the a1 times x minus x0. So this is a short expression. Simplify the expression of p and x using the divided difference notation. Okay, and then note that the value of the kth divide difference is independent of the order of numbers x0 to xk. Yes. Okay. So now next one, and then so now we're gonna see how to design the algorithm for finding divided differences. So to obtain the divide difference coefficients of the interpolatory polynomial p of x on the n plus 1 distinct numbers x0 to xn, these are nodes, right? So input must be x1 through xn plus 1, and then output must be f of x1, I mean f of x1 and f through the fx sub n plus 1. These are input. Okay, so keep in mind this. These are actually nothing but what? F of x1 must be what? F of x sub 1 through the f of xn n plus 1. These are must be zeros divided differences. Okay. Okay. So now, let's see. Okay. So now, what are you gonna do? Let's see. Similar, in similar what we did in David's method, we're gonna construct the matrix. Okay, we're gonna store the all of divided difference in a matrix. Okay, so let me see. Okay, give me a second. Okay, so here, so the output must be n plus 1 by n plus 1 matrix. Okay, so F, let me do it like this. So F, okay, this is n plus 1 by n plus 1 matrix. So the first column must be F of x1. Okay. Okay, here x sub 1 must be x sub 0. Okay, so I just modify, I mean, yeah, I just modify the algorithm to be comparable with the MATLAB. Okay, so that's why the size of matrix is not just n by n by n. Okay, it's just but n plus 1 by n plus 1 because index should start from the 1, not 0. Okay, so f of x1, f of x2 through d1, f of x n plus 1, because n plus 1 nodes will be given, and then their function values must be given. Okay, so these are actually nothing but what f of x, the function value at x1, function value at x2, and function value at x sub n plus 1. Okay, so now the key mind is this one is what actually f of what x0. This one actually what f of x1. Okay, this is actually what f of xn. Okay, key mind is. Okay, so now next one, using these f of x1 and f of x2, we can compute the what the first, the first column. These what the first column is zeros, a divide difference, right? Okay, divide is difference. All right, and the second column going to be what first divide difference. So this is going to be f of x1 comma x2. Okay, and then f of x2 comma x3. Okay, through the f of xn minus 1, n comma n plus 1. All right, and then using these two columns, we can compute the second degree, a second divide difference, f of x1, 2, and 3, and the f of x2, 3, and 4. Oh, okay, through the what f of x n minus 1, f of xn, and then xn plus 1 bracket through this. And the last row and the last column will be what f of x1 through the f of xn plus 1. Okay, and then all these are going to be diagonal entry. These are a diagonal entry, and then all the entry above the diagonal entry going to be 0. Okay, all right, and then actually the first diagonal entry is what? That's going to be A0. And then second diagonal entry going to be what? A1. This is going to be A2 through the what? This is going to be what? AN. Okay. So that's what we want to construct. That's what we want to find out. Okay. So the algorithm in the lecture note will generate this function, this matrix. Okay. So back to the lecture note. So oh, not this one. So give me a second. Yeah. So all right. So now then, the first column of the matrix F should be what? F of x. should be this, right? Okay. Okay. And then now the step one, yeah. So this is the this is index of row. Okay. So start from 2 to n plus 1. It makes sense, right? And then j, this is index of column. Okay. So j goes to j move from 2 to I, and then we find f of I comma j, which is this. Okay. So yeah, so let me clear. So let me explain the code. So how come? Because see that in here? Why the I mean I goes, so here for I goes 2 to n plus 1, and then for j goes 2 to I, okay, and then set f of I comma j is equal to fi comma j minus 1 minus fi minus 1 comma j minus 1 over xi minus j plus 1, and then end and end. How come? Because the first one, yeah, this is exactly the same strategy what we use in a Navier method. Okay, in a matrix, so we want to calculate the what? So since the first column is given, so from the next column we need to compute the what? The second column. We need to compute from the second column to the what? Diagonal entry. Okay. So for the second row, we compute the just diagonal entry. Okay, third row, we need to compute the what? Second column, entry in the second column, and then diagonal entry, right? And the fourth row, we need to compute the what? The second column, third column, and then diagonal entry. Okay. So the I start from 2, yeah, makes sense, because we start from second entry. We need to compute this one first, right? This is second entry. Second row, okay? We need to compute the from that entry, which is in the second row. So that's why I start from 2. 2 n plus 1 means that I told you I is the index of row. So I is just moving from second row through the last row. Okay. While I is moving from 2 to n plus 1, j moves from 2 to I, 2 to I, yes. Okay. From second column to the what? Diagonal entry column. Okay. So up to from here to diagonal entry. Oh, here. Okay. From here to diagonal entry. From here to diagonal entry. From here to diagonal entry. Okay. So now then, what about this? Okay. So look at this. So f of xi comma, let's just figure out the formula of that divide difference. This is equal to what? F of x what? 2 comma 3 x comma 3 minus f of bracket, sorry, x comma 1 x comma 2 x of 2 over the what? X what? x3 minus x1, isn't it? Okay. So now excuse me. So then for here, so the fi comma j, then we what? This is what? So right here, f of oops, f of x sub 1, x sub 2, x sub 3. We to calculate to compute this, we need the two information in a previous column, right? F bracket x sub 1 comma x sub 2, and then f of x sub 2 comma x sub 3. Now let's figure out the what the x the indices of the entry of three informations. This is equal to what? F of what? The you see that this is the third row and then third column, right? Okay, so third row, third column, F of 3 comma 3. This is gonna be F of the second row, second column. And this is gonna be what? F of the third row and second column. You see? Okay, so these two guys have the same row. These guys are on the same row. Okay, you see. So now, then this is equal to, I told you, we could say F of 3 comma 2, third row, second column entry minus this what? Second row, second column, right? Entry. F of 2 comma 2 over, okay, and then x of 3 minus, okay, then x and let me say x of 3 minus x of 1. Okay, if you just generalize this one, then you see that here, that I mean the index of row in the first term in the numerator must be equal to the index of that index of row of this one, right? So here I, that must be I, right? Okay, and then the 2, this is the index of column of the first term must be 1 less than the index of column of this, so which is j minus 1. And the 2 is what? No, the index of row in the index of row and the index of column in the second term must be 1 less than index of row and index of column here, this one. So I minus 1, j minus 1. You see that? And then the what? Actually, the x what? The x of 3, the index of the what node here must be equal to what? The index of the row. So x of I. Okay. And then what? Now next one is to get the x of 1, we subtracted 3 from I. We subtracted the 1 from 3. Oh, I'm sorry. Give me a second. To get the x of 1, we gonna subtract the 3. I mean index of subtract the index of column from index of row and then plus 1. Okay, then we're gonna test. Okay, so if you yeah, if you just yeah, okay, so I mean yeah, that makes sense for this example. But what about other examples? So please try to apply this one into the other entries, okay, or this here or here, okay. So try to figure out whether or not this you know, this formula is really work for other entry. Just please try that, okay, by yourself. Okay, so now then let me see. Oh, not this one. Give me a second. All right, so now then, okay, so okay, we understood this double loop, right? All right. So we know that the diamond entry, all diamond entry must be stored in a coefficient. Okay. Right. So now what's next? And next one, so this algorithm will should generate the should return the what? The value of interpolating Lagrange interpolating polynomial at a certain x value. Okay, so output is the, give me a second. Oh yeah, okay. So yeah, I'm sorry. So this one, yeah, okay. Sorry. So this code just will generate just a coefficient of the algebraic expression of Lagrange interpolating polynomial. I'm sorry. So the output must be coefficient COEF, which is nothing but list of the diagonal entry of matrix F. Okay. All right. So give me a second. So okay. So see. All right. Okay. So I already wrote the code. Okay. So divdif, that's the function name. So right there. Okay. So in this function, okay, so give me a second. Okay, in this function, this M file will return the three outputs: matrix F, was we talk about, right, and the coefficient, and then Pn. Pn is approximate. I mean, the value of Lagrange polynomial p of x, p sub n over x at a certain x value. So t is the input, okay, and then not like the other function, the algorithm we wrote. So input the data value. Input is in the M file, okay. But let me change it. So let's say t data, okay. So we make this one to the comment. Oh, I'm sorry. It should be this. Okay. So now then, let's see. Oh, sorry. So the input, I mean, let me write the name of code, okay? Divided differences, okay? And the input is what? The x value, t, okay, which is x value, okay? And then data, that is the nodes and what? The f of nodes, okay? The output must be what? F matrix of divided differences, okay? Right, and then the coefficient, which is the a sub 0 through the a sub n, okay? Then the p sub n, pn, that's the what approximation at t, okay? So now the let's see, okay. Now first one, we need to figure out the size of the, I mean, number of nodes, okay? So we use a command the size. The size will return the what? The number of row, number of column in data. Okay, and then one means the what? That indicate the number of row. Okay, so the key one is data must be here. Data. Let's see. Data must be data, that must be what? 2 by, n by 2 matrix. Okay, keep in mind this. So now so that's gonna be determine determine the size of nodes. Okay, so we got this. Then also we determine what, and then set. Give me a second. Oh, what happened? Give me a second. Yeah, set the size of matrix F. Okay, so F is zeros, m by n. Okay, so now the coefficient is going to be m zeros m by 1. Does it make sense? Okay, because coefficient is nothing but what? The coefficient, we're gonna put the diagonal entry in matrix F. So the size of coefficient must be m by 1. Okay, and then excuse me. So now next one, we're gonna extract the nodes and then put the nodes into the variable x right there. And then f of x, that's the function value at nodes, which is the second column of data. Okay. Then you don't have to, just take care of this part. Okay. Just right. So now then, next one is what about this? The f of x, f of e, v, l, and f. So for sometimes, if a function is given, then we can evaluate the function at nodes. We can find out the function value at nodes by evaluating f given. Okay, by just plugging the nodes into f. Okay, so but in this case, function value is not given. Okay, so we don't have to do this. Now the what does that mean? F of all the now we put the f of x into the first column of the matrix F. Okay, and then just this is exactly the same as the algorithm. Pseudocode in the next note. Okay, all right, and then now next one. Then what about Pn? Okay, so what's the Pn was what? Pn was the on this. Give me a second. Pn. Now we compute p sub n of t, which is equal to a sub 0 plus what, a sub 1 times t minus x sub 0, and then plus a sub 2. You understand what I'm saying? T minus x sub 0 times t minus x sub 1 plus, and so on, right? So the Pn gonna be what? Actually, first one we gonna put a sub 0 into p sub n. Okay. So, but a sub 0 is nothing but the a sub 0 is what? Is in the first entry in a column vector coefficient, COEF, right? Okay. So you don't have to take care of this. Okay. So okay, I'm sorry. So what if a t is not a single real number, but t is a vector? Okay, then we need this. Okay, so give me a second. What that means? second. It means this. Look at this. Then the f. What? So the p sub n of t. What if t is a not a single number, single value, but a column vector? Okay, let's say t. Okay, let's say this is here. Actually, t is like this: t sub 1, t sub 2 through the t sub k. Okay, then that is equal to p sub n of t sub 1 through the what? P n sub n t sub k, isn't it? This makes sense. Well, that is equal to what? A sub 0, right? Plus a sub 1, t sub 1 minus x sub 0 plus through here. And then a sub 0 plus a sub 1, t sub 2 minus x sub 0 through the what? A sub 0 plus a sub k, and then t sub k minus x sub 0 plus 3. You see that? Okay. So now then, in the command, in my code, the command, the p sub pn is equal to coef of 1 plus times ones, and then size, and then t comma 1 comma 1. What that means? Okay, we need to then first of all we need to construct this one. Okay, but this is equal to what? Nothing but what? Give me a second. This one is equal to what? A sub 0 times 1, 1 through the 1. We can say that, right? So this is the kind of the what? K, the K by 1 matrix or column vector with a K entry, right? So how can you construct, we know that how to generate the matrix filled with 1, which is the command ones. Okay, and this is the what? A number of row. This is a number of column. The matrix filled with ones. Okay, so now then what? What's the number of row? In this case, what? The number of row must be equal to number of what? Row, the input t, right? Okay, so we do this. Okay, the size of t comma 1 to give us the size of t to give us what? Number of row and number of column, but we pick the 1, so we comma we just the type the comma 1 that will give you the what number of row, the matrix t. Okay, and that's going to be number of row in a matrix filled with ones, and then number of column must be 1. Okay, so this is equal to nothing but what? COEF 1 times actually what? 1, 1 through the 1. Okay, and the number of the entry, which is number of row, must be equal to what? Size t comma 1. Okay, so now then the next one is this: for k is equal to 2 to n. Okay, b. All right, so we construct b. What's b? Okay, so right there. Now we constructed. We're gonna generate this one. Let's say this is b. Okay. Okay. I mean this is b. I mean these are b. Okay. So then what we're gonna do. So the k equals 2 to n, and then b is equal to ones, and then size t comma 1 comma 1. Okay, what does that mean? This is what? That means what? Just 1 1 through the 1. Okay, that one nothing but the column vector filled with the 1. Okay, all right. Okay, now for I goes 1 through the k minus 1. Okay, now, and then for b is equal to B, and then this is a matrix operation, right? And then T minus, the separate operation, right? T minus X sub I. Okay, what does that mean? This one means that what? First one, B dot, okay. This is what? This is the column vector, right? This, okay. 1 through the 1, okay. And then dot times T minus Xi is what? The T1 minus X, when I goes 1, we got this. T1 minus X sub 1 through the what? T, in this case, T sub n, right? T sub n minus X sub, in this, the code, give me a second. Let me see. Let me say T sub, let's say T sub m, okay? Because here I just use a K, but in my code, I already use a K, okay? So I just changed the number of the size of T as m, okay? So, okay, like this, right? So now then, this is what? Then we'll get just T, that and then multiplication means what? Just multiply the 1 and the first row, first entry times first entry, and then second entry times second entry, okay? It's not the dot product, okay? So that will give you the what? Just this one, okay? And then we here end. This is a what? For loop, right? So we keep this one, right? Or we're gonna keep this one while I is moving from 1 through the k minus 1. So finally, we're gonna get the what? That for loop will get the what? T1 minus X sub 1, okay? Times the T1 minus X sub 2, is it? Through the what? T1 minus X sub k minus 1. Okay? You see that? Right? But what's the k? K is moving 2 to n. You see the k is moving 2 to n. So finally, we're gonna get this. So for k goes 2 to n, then b is equal to 1's size t comma 1 comma 1, and therefore I is equal to 1 through the k minus 1, and then b is equal to b dot multiplication t minus x sub I, okay, and then pn is equal to pn plus coef of k times b, and then end. So when k equals 2, then k is equal to, then what? P, we're gonna get the b gonna be, k equals 2, then I goes just 1, move from 1 through just 1, right? So b gonna be just what? T1 minus x sub 1 through the what? Tm minus x sub 1. And then Pn gonna be what? Pn gonna be A0 plus, okay, what? COEF2, which is the what? A1, right? A1 times B is what? T1 minus x sub 1 through the A0 plus COEF2 times Tm minus x sub 1. Okay, I see. All right, that's the, so it makes sense, right? Okay. Okay. So now next one, k equals 3, then b gonna be what? B gonna be T1 minus x sub 1. Okay, So x of 1 is nothing but x0, okay? This is nothing but x0. Then t1 minus x of 2 through d1, tm minus x of 1 times tm minus x of 2. So pm gonna be what? So pn is gonna be a0 plus the 1 times t1 minus x of 1. That was in the we got this one in the, that was stored in pn in previous loop, previous iteration, okay? And then we add this one plus, because obviously plus, right there, plus, okay? This is plus, and then coef2 times t1 minus x of 1 times t1 minus, okay, is minus x of 2, like this. Okay, that's the meaning of the code, this one. All right. So second. Okay, so now then we compute the approximation p sub n. Okay, so the we define here the 43 to 43 to line 45. You can ignore that. Okay, so okay, you don't have to consider that. So if you let me give, okay, so let me give you an example. All right, so now, okay, so data, let's say, okay, okay, so now, so let's say this data is given. Okay, I mean, data is this. Okay, so first column, first column is represent the nodes, and the second column represent the function value, data value. Okay, so now then f coef my pn. I mean, by the way, t we define t is equal to let's say 1.1 and 1.4 and 1.2, okay, and then 1.4 and 1.5 and then 1.7 and 1.8, okay, and then 2 and 2.1. If you have to put prime, okay, otherwise you're going to get the row vector, but we need a column vector. Okay, now we enter those two input into the function f coef and then pn to dvd if and then t comma data. Okay, so the pn is this. Okay, so these are what the value of Lagrange interpolating p nth degree Lagrange polynomial of p. Okay, with the at the these values. Okay, all right, so now let me see. Okay, give me a second. Okay, so now what about the error estimate? So let's see theorem 3.6. Suppose f of x is in Cn space and the x0 through xn are distinct numbers. Then there exists psi generally unknown in a inner a comma b with the let's see yeah, this guy, this is nothing but a sub n, right? Okay, then this is equal to f of sub n derivative to f over n factorial. What that means, then an, okay, So the absolute value of a and a sub n is bounded by the maximum. You see the maximum of the nth derivative f, because psi is generally unknown. Okay, so then we need to find out the absolute maximum of nth derivative f on the closed interval a comma b. Okay, so maximum of f of n. Okay, absolute value of f the f of n, nth derivative f, nth derivative f. Okay, over n factorial. Okay, so this theorem gives us the upper bound of the coefficient a sub n. Okay, so I'm not gonna go over the proof. Okay, so just read the proof if you're interested. Okay, so and then next time, let me see. Okay, next time I'm gonna cover the Newton's divided difference formula with the equal spacing, and then the forward and backward difference. Okay, cover. Okay, briefly. Okay, yeah. Let me stop here.